Hey there, Cool Fire listeners! Welcome back to another episode of Cool Fire News, Weekly Edition, where we break down the tech shaping tomorrow into stories you can understand today. I'm Siri, and today we're putting on our tool belts and thinking caps, because we're diving into something hands-on, robot assembly and programming. If you've ever dreamed of building your own robot, whether it's a simple line follower, a robotic arm, or even a humanoid assistant, this episode is for you. Let's get started. So, what does robot assembly actually mean? At its core, it's about putting together the physical components of a robot, from mechanical parts like frames, wheels, and gears, to electronic parts like sensors, actuators, and microcontrollers. Think of it as building a body. The programming, which we'll talk about shortly, is what brings that body to life, like the brain and nervous system. Whether you're assembling a kit like LEGO Mindstorms or building from scratch using servos and Arduino boards, the assembly phase is where the robot begins to take shape. Let's talk about the essential components you'll typically assemble in a basic robot. 1. Chassis or frame. This is the robot skeleton. It holds everything together and gives the robot its shape. 2. Actuators. These are motors or servos that move parts of the robot. They allow wheels to spin, arms to lift, and joints to bend. 3. Sensors. Robots need eyes and ears. Sensors detect things like distance, temperature, light, motion, or orientation. Common ones include ultrasonic sensors, infrared sensors, gyroscopes, and encoders. 4. Controller processor. This is the robot's brain. Popular options include Arduino, great for beginners and hobbyists. Raspberry Pi offers more computing power. Microbit or S32, lightweight and wireless capable. Industrial robots use PLCs or embedded control boards. 5. Power supply. Usually batteries are external power sources. Choosing the right voltage and capacity is crucial to avoid burning out your components or underpowering your motors. 6. Wiring and PCBs. The nervous system. Cables, connectors, breadboards, and sometimes even custom PCBs, printed circuit boards, are used to connect everything. Once all this is assembled, the frame, motors, sensors, and brain, your robot is physically ready. But it can't do anything yet. That's where robot programming comes in. Robot programming is what gives your robot purpose. It tells the machine how to behave, when to act, and what to do when something changes in its environment. There are two major categories of robot programming. 1. Low-level programming, embedded control. This is where you write code that directly controls hardware, like turning motors on and off, reading sensor data, or blinking an LED. Languages commonly used: C++, Arduino, STM32, MicroPython. Assembly, rare, but ultra-low level. 2. High-level programming, behavior and control. This is more about strategic behavior. For example, navigating through a maze, picking and placing objects, following a line, avoiding obstacles. Here, robots can use libraries, APIs, and even AI or machine learning tools. You might use Python with ROS, Robot Operating System, JavaScript for web-controlled bots, MATLAB Simulink in academic and research settings. With more complex robots, you can program behaviors using state machines, control algorithms, or neural networks. Now here's something super important. Programming is not one size fits all. Different types of robots require different approaches. Let's break a few down. Mobile robots focus on motion control, obstacle detection, and path planning. Robotic arms involve kinematics, joint control, and precision handling. Humanoid robots require balance, coordinated motion, and sensor fusion. Drones need flight stabilization, GPS integration, and real-time feedback. Each of these requires different sensors, actuators, and software stacks. Here's a question people often ask: how do I test if my robot is working? The answer is incrementally. Start with the basics. Can you power it on? Can you blink an LED? Can the motor spin? Can the sensors return data? Then slowly build up behavior. For example, move in a straight line, detect and stop at a wall, turn 90 degrees, navigate around objects. This process is called debugging, and it's a huge part of both assembly and programming. It helps you identify whether a problem is hardware-related or software-related. Let's take a quick break with a little cool fire quiz. Question 1. What is the function of an actuator in a robot? A. Store data. B. Process input. C. Create movement. Answer: C. Actuators are responsible for movement. Question 2. Which of the following is not a robot controller? A. Raspberry Pi. B. Breadboard. C. Arduino. Answer: B. A breadboard is for connecting components, not controlling them. Question 3. In what language is Arduino usually programmed? A. Python. B. C++, C Java. Answer: B. Arduino sketches are written in C or C++. Before we wrap up, let's talk about robot programming tools and environments. 1. Arduino IDE for programming Arduino boards. Lightweight, perfect for learning C++ basics. 2. Python with Thonny or VS Code. Great for higher-level programming and AI. 3. Scratch Blockly, visual programming for kids and beginners. 4. ROS, Robot Operating System, the industry standard for research and advanced robotics, used in everything from self-driving cars to humanoid bots. 5. Simulators, tools like Gazebo, VREP, or Webbits let you test your code in a virtual robot before trying it on the real one. Simulation is especially important when your robot is expensive, or when crashing it would be less than ideal. So, let's bring it all together. Robot assembly is the physical creation. Robot programming is the digital soul. Combine both, and you get a functioning, intelligent machine that can move, sense, decide, and act. Whether you're building a sumobot for a school competition, an automated vacuum cleaner, or an industrial arm for manufacturing, understanding both assembly and programming is key. That's it for this week's episode of Cool Fire News, Weekly Edition. We walked through the fundamentals of robot assembly and programming, covered tools, components, languages, and best practices. Hopefully, you're one step closer to building your own robot army. Or at least a really cool one that doesn't bump into walls. Next time, we'll explore human-robot interaction, how robots and humans can work side by side safely and efficiently, and the tech that makes that collaboration possible. As always, don't forget to follow, rate, and share this episode. Stay curious, stay creative, and keep building the future one bot at a time.